Beginning of 2024, everyone's talking about AI. And a lot of the news out of reInvent in 2023, only a few months ago, was around AI. And some of that news was around the kind of custom silicon that powers some of these workloads, which I thought was very, very exciting. But in addition to all of the news that everybody gets to see, some of my RedMonk colleagues and I got to take a tour of Annapurna Labs in Austin, Texas recently. Annapurna was kind of acquired by Amazon, I believe, in 2015. And so we got to see some really cool things and geek out. And we now have questions about custom silicon that we did not have before. So joining me today is Chetan Kapoor from AWS, who's going to answer some of our very geeky questions about custom silicon. To start us off with, Chetan, can you just tell us a little bit about who you are, what you do, and what custom silicon has to do with it?
Yeah, absolutely. So hi, everybody. Chetan Kapoor here. I'm with AWS and the EC2 product management team. And I run our hardware accelerator business. So this basically entails EC2 instances or compute platforms that feature some sort of a hardware acceleration. Could be GPUs, could be custom ML chips that we're building. Or other forms of accelerators, right? And I've been running this business for coming up on 8 years now. It's been a while.
That rounds up to a decade, yeah, in case you were wondering.
It does, yeah, especially in Amazon years. Yeah, things go by really, really fast. And yeah, it's been a fascinating space. There's been a lot of coverage around the types of models that companies are building, and the type of end user capabilities that we're experiencing on a daily basis these days. But the space that I operate in is all about providing the required compute infrastructure to support these customers building these type of models, right? So there's a lot that goes into providing infrastructure to support somebody building a foundational model, right? And that's the space I mostly operate in. There are other businesses that I also support, specifically in the HPC and the graphics and gaming space. As you can imagine, those type of applications also leverage accelerators for a lot of different workloads.
So it sounds like you are very busy because you have a lot of things under your supervision or direction. Thank you again for taking the time to chat with me today. I'm going to jump right into questions because I have many of them. In fact, we had to narrow down the list of questions that we would ask you, so this would not take 2 hours. But to start off with, one of the core themes that came up throughout our tour of Annapurna Labs was spending engineering resources where it matters most, especially around build versus buy decisions. This theme was visible in multiple aspects, including the strategy of your hardware design and components used, and also the lab operations themselves. When it comes to custom silicon, can you give us some context around the areas where AWS chooses to build and how they are areas of differentiation for AWS? Or in other words, how does these build versus buy decisions kind of relate to specific outcomes in which AWS is investing?
Yeah, so this is a super interesting aspect of talking about how we build and deploy these products, right? So if you look under the covers and take a look at an accelerator for training a large language model, as an example, right? A lot of the core function comes around being able to do large matrix math operations really, really effectively. And that's where the heart of the chip lies, is being able to do lots and lots of matrix multiplications really, really quickly, right? Because essentially, for training or even inferencing of a large language model or a deep learning model in general, that's one of the core compute functions you need, right? Now, when we start to look at a design, we were like, okay, what parts of the design we think we need to invent IP for and bring a lot of value for? A lot of this is going to be centered around the compute engine. It's going to be centered around how the compute engine talks to the memory that's available, because it's not just about compute, it's about memory also. But there are a whole bunch of other things you need in a chip to actually enable that chip to operate. Like, for example, power subsystems, for example, high-speed interfaces, right? Out-of-band communication mechanisms. And those are some of the components that we can actually get some help from third parties and leverage their IP instead of reinventing, high-speed interfaces or, PCIe controllers and things like that, right? So when it comes to like build versus buy, our core focus is around, okay, what is the key capability that we need to build that is not available in the industry, right? And then how can we impact our time to market? Because, of all this craziness in the Gen AI space, everybody wants to get their next application and model up and running quickly. So there's a lot of pressure from a time to market angle, right? So if we can leverage an IP from a third party, from a partner, then great. That's going to enable us to get to market quicker, right? And obviously the third aspect is cost, right? So we have to be mindful of like, okay, how much is going to cost us? What does that translate to the economics and benefit of the customer? And that's where all these three things have to balance out, right? It needs to be IP that we can uniquely build and deliver value. And if there's ability for us to leverage third parties, great. But at the same time, we need to be mindful of what it costs us to build in terms of engineering time and effort, and obviously the cost of silicon itself, right? So those are the kind of vectors and areas we need to kind of think through when it comes to the buy versus build decision for elements of a particular silicon design.
Yeah, and that makes sense. And I think that the balance has to be tricky at times, especially when you're getting into the desire to make everything as perfect as possible versus the time versus and the cost kind of factors as well. And I think, so saying that from the position of say where you are, and then being one of the people in the lab who's like trying to navigate these decisions as well, I think has to be a little bit different. And I want to kind of talk about those build buy versus buy decisions in the context of the lab. And before we did our tour of Annapurna Labs, it had been described to us as a startup-like environment. And it also had been described as scrappy a number of times. And when you walk in, it does feel that way. It's delightful. And also it was evident in things like the machine that tests cards running in part with Raspberry Pis, but also in team members having to pick up all these different things like, oh, now you have to go learn how to use a soldering iron if you don't before, and a microscope and cabling, or understanding the latest wave of compute demands around AI and ML. How do you build a team that has this like scrappy ethos that fosters this building mentality and creativity while also ensuring that it's latest focused and selective and not kind of unnecessarily reinventing wheels?
Yeah. We have internally, we have a saying that Amazon is the world's largest startup. Many parts of our business is true. In some cases, we're not. But, the overall mental model, just comes down from how we think about teams and ability for teams to control their own destiny, right? You might have heard us use the reference of two pizza teams. And for those who are not familiar, it essentially represents a team that is small enough that if you had a happy hour, you can get like 2 XL pizzas, and you'll be able to kind of have that happy hour with just two large pizzas, right? And so it essentially means that the team is about 10 to maybe 15 people, and they're super nimble, and at the same time they have the ability to control their own destiny, right? So from an org structure perspective, when we think about how we set up teams, we want to make sure that the teams have the ability to work on the things that directly translate to a positive impact in specific influence, a specific area that they're operating. There's some other cultures out there where teams have a whole bunch of dependencies on other teams, right? So like if you want to get a product done, you need support from X, Y, and Z teams and things like that. So fundamentally, there's a pretty different culture at Amazon, and it's even more pronounced in the Annapurna team, right? So Annapurna is a startup within a startup. Kind of think about that, right? So that's why we have small teams that are focused, and you talked briefly about this. Like we hire builders that are naturally multifaceted, right? Where if there's a person who is designing the hardware, a person is also responsible for bringing it up, like getting all the testing around it to make sure that it is running. Because the other perspective we have as Amazon, especially in Annapurna, is that if you're building it, you should be testing it. Like it shouldn't be that there's another team that are responsible for testing and then you're going back and forth across those two teams, and maybe you don't have a really clear understanding of how the product is supposed to work, and there's some loss in translation and things like that. So organizationally, there's a lot of emphasis at Amazon and Annapurna to make sure that we've got the super nimble teams. And you mentioned a little bit about Raspberry Pi. That's a really good example where, the team needs, a way, and, this came about in COVID especially, if they need a way to talk to pre-production silicon that is only available in the lab. Ideally, you would just come in the lab and actually just work with the silicon in person. But if you don't have that ability, where again, think about COVID, where a lot of people couldn't come into the office or didn't want to come into the office, we empowered them to make decisions, to have scrappy environments, but at the same time, ensure that it's secure and reliable in the way it's kind of set up, right? So in the case of Raspberry Pi, we actually use that to power some of our supporting circuitry around the chip, and have an interface to kind of talk to that chip, right? So that particular Raspberry Pi that you saw was set up in a controlled environment where it wasn't accessible as a device on the internet. You needed to have restrictive access to have access to it, but at the same time, it is an off-the-shelf part that the team was able to kind of leverage and set up the test bed in order to make progress on the chip validation. Right.
Yeah, and it's very cool. And the lab, it does have the feel of a startup, the two pizza team, but with the backing and the almost like security resources available to
large enterprise,
which is I think exactly what you want, right?
Yeah.
So shifting gears a little bit to talk about kind of training and inference workloads and the chips that power them, and maybe the different needs that these type of workloads have. During our tour, we had the chance to see Trainium and Inferentia chips. Can you tell us a little bit about the difference of, kind of between the workloads for which these chips are designed, and how and why are the infrastructure requirements for training workloads different from inference workloads? Because one thing I learned is that they are very different.
They are. And they're very different. And, a lot of the engineers, don't have a true appreciation of what the differences are. And generally speaking, if you look at training versus inference, training is a scale-out workload. By what I mean by that is for a deep learning model, and especially all these large language models, you're not training a model on a single chip. You're usually training it across hundreds, if not thousands of these chips, because you want to get the training job done as quickly as possible, right? And on inference, on the other hand, you want to make it super cost effective, because if you're going to be supporting millions of inferences on a per day or per minute or per second basis, you need to make sure it's super optimal, right? So inference, for the most part, and it's changing actually in the market right now, is a single chip or a single server type of workload. You don't scale out a single inference job across hundreds of chips or thousands of chips, right? So because of that, you have unique requirements at the chip level, at the server level, and also at the data center level across training and inference, right? So when it comes to training, to look at specific details, you need a lot of high bandwidth memory. You need a lot of chips that are interconnected using high performance networking. And you need to have really, really fast storage, because you need to feed data into this training compute cluster. Otherwise, your expensive chip resources are going to be starved, right? So there are differences at the chip level where you need tons of compute, tons of memory kind of packed into a single chip. And then you need a lot of networking and storage to kind of combine it all together to form a large clusters, right? Very large clusters. And on the inferencing side, for the most part, you are going to be sensitive to performance, because you want your interactive experience to be super interactive and snappy, right? If you're talking to a chatbot, you want your responses right away. You don't want to say something into a chatbot and wait 10, 15 seconds for it to kind of respond, right? So customers end up optimizing for latency and throughput, and also cost, right? So inference used to be a single chip workload, right? So if one customer is interacting with a chatbot that is typically used to run on a single chip, and it was good enough for the experience. But now with the LLMs and especially the GPT-3 and 4 type of models, where it is kind of scaling out, where you actually need multiple chips to host that model and actually provide a compelling experience for the customers, right? So to kind of summarize it, it's the big difference is scale out versus scale up, right? Where again, for training jobs, you need hundreds and thousands of accelerators that are tied together. And for inferencing, it's typically limited to a few chips, and then but at the same time, it needs to be effective and both from a performance and a cost standpoint.
Yeah, that makes sense. And for me and my colleagues, I think the visuals of seeing the different kind of board setups for like the Trainium and the Inferentia chips was really impressive. And I think what really struck us too is we got to see, I think, a Trainium 1 and an Inferentia2 chip, and and they look very similar, but the boards they're on and the servers they're set up with vary so greatly. And can you just speak a little bit about that? I know you kind of touched on the different requirements for like my previous question, but can you tell me more about why these things look the same but they're situated so differently?
Yeah. So that's a really good example, by the way, right? So on Trainium 1, the part is the chip is designed for, as you can imagine, for training, right? So we have to max out the compute performance that is available on the chip, and we have to make sure that within the server we have as many chips as we can pack in, and interconnect those chips really, really tightly, right? So a Trainium 1 server has 16 chips running at full power that are all interconnected with each other, right? So again, it's optimized for training where each chip needs to be able to talk to the other chip, and we need to max out the performance, right? Now for inference, as I mentioned earlier, right? Inference is a super cost-sensitive workload, and usually it's bound to a single server, right? So when we were designing the brand new architecture, our second generation architecture, we were like, okay, we've got a single architecture, we got to support training, but we also at the same time we want to look at supporting inference on leveraging the same architecture, right? So on the inference side, we took the core silicon and we tweaked it where we get lower cost structure, dial down the compute performance a bit because that was really not required for us to kind of max out for Inferentia2, and also change the interconnects for chips to chips. So instead of having like an all-to-all connection, Inferentia2 as a server has a ring that connects all the 12 accelerators that we have, right? So there were pretty fundamental differences at the board level that allowed us to have multiple chips come out from the same architecture to support training and also inference, right? So yeah, your observation was correct. The fundamental silicon is very, very similar between the two. They leverage the same architecture, but they are packaged in a very, very different format, based on the requirements of training versus inference.
And then, if you don't mind speaking about this, so Trainium 2 announced at reInvent. Anything about and that chip itself, I think the kind of benefits were kind of touted and shouted from the rooftops. But going beyond that, in terms of like the kind of setup around it, anything about that we should know about?
Yeah, I think it's going to be super exciting for our customers, and we're really pumped about what that chip is going to bring to the market. Some of the high-level things we mentioned when we announced that part was we expect for it to be 4 times as performant as Trainium 1, right? So that's pretty sizable. We're also going to set up really, really massive clusters of Trainium 2 chips, right? So, we talked about, workloads needing hundreds to thousands. We're starting to see customers today that are running tens of thousands of these chips in a single cluster. And we expect that trend is going to continue, right? So we're planning on deploying Trainium 2 as part of massive clusters. And that's going to be really exciting for some of the leading builders of foundational models, right? And we're going to disclose more about Trainium 2 in the coming months as we get closer to preview and eventual GA. We'll share more details around how we expect to package it as an EC2 instance, and the kind of clusters we expect to be able to kind of provide our customers to enable them to train these next generation foundational models.
Well, I, for one, will be on the lookout for that news as it rolls out, because I think we're at a point where the stuff that is running the workloads that we need to do the things we want to do is becoming more and more important.
Yep.
And it's kind of speaking on that. So RedMonk, we care about developers very much. Many of the software developers we speak to are not overly conscious about hardware. And that may have to do more with the nature of their training, like what they're taught to do and what they actually need to do their jobs than anything else. But from your perspective, why should developers care about silicon? Because like clearly I do, we do, but why should developers care about it?
Yeah, so there are multiple reasons, right? So if you're in the AI/ML space right now, there's a lot of focus on time to market, which is understandable. People want to tap into this new innovation in the market and try and deliver meaningful results and improvements to the businesses, right? We totally get that. The reason why paying attention to silicon and the underlying infrastructure is going to come down to performance, cost, and ability for customers to kind of control their own destiny, right? What do I mean by that, right? So, if you're building on GPUs today, as an example, right? That's going to be great. That's going to allow you to kind of move quickly, but at some point, the cost of training using the existing methodologies is going to just skyrocket, right? It's going to be at a point where the business leaders in your customers' companies are going to start like, okay, well, you're consuming tens of thousands, hundreds of thousands, of millions of dollars to kind of train these particular models. Are we actually seeing the ROI on this investment or not, right? If your developers are conscious about how they're training their models, what softwares and frameworks they're using, it'll give them the ability to kind of try out alternative architectures, such as Trainium, maybe, or maybe something else in the future, right? And enable them to either get to market quickly or potentially save 40-50% of the operational costs, right? Which can be substantial, when it comes to like training these LLMs, right? So it is super, super important for customers to be cognizant about how they're building their applications, because what we are seeing in the market right now is that there are certain set of customers that are writing code directly to a vendor's API, right? So they're like, okay, I'm going to pick a vendor A and I'm going to use their software libraries, and my code is going to have a dependency on that particular software library, right? So they're for the most part, they have a direct coupling to vendor A in this example, right? The alternative that we're seeing also is that where customers are using levels of abstraction, but they're like, oh, okay, you know what? I don't want to have a direct tie-in with the vendor's library, so I'm going to use an open source platform that's going to give me a level of abstraction. So what I'm referring to is common machine learning frameworks like PyTorch and JAX, where if you're leveraging these frameworks to actually build and train and eventually deploy your models, you're going to have that flexibility where, down the road, if there's a vendor B that is providing a different hardware platform that is more, more aligned with what you're looking for from an economics or performance standpoint, you will have the ability to kind of try the vendor B and see how well it works for your business, right? And alternatively, you'll have the ability to kind of move back also, right? So developers need to be super conscious about how they're building their applications, what platforms they're leveraging, and what ability will they have to actually try out different silicon from different providers in order to either optimize the time to market or optimize their costs, right? That's the most fundamental thing. There's a lot of detail also around the specific feature and capability that a particular part might provide, right? So like if you're optimizing inference performance as an example, right? There are a whole bunch of like techniques that are available at the hardware level to optimize the inference performance. Same thing on the training side, right? So being aware of like what hardware platform you're leveraging, will also enable you to kind of micro optimize the performance and eke out the most performance out of that platform, right?
Yeah, you're definitely speaking my language, especially talking about concerns with like time to market and velocity and abstraction, which more and more we're seeing the developer tools and the different ways they interact with the world, like being kind of mediated by abstractions, like kind of more and more. So we've spoken a bit about why software developers should care about hardware. How is AWS making it easier for software developers to think about hardware, and where and how does abstraction come into play?
Yeah, so that's there are a couple of elements here, right? So one is around the AI/ML space. So when it comes to Trainium and Inferentia specifically, we have put in a lot of effort in taking our compiler, which is called Neuron, and plugging that under common machine learning frameworks, right? So again, going back to our earlier conversation where we want to make it easy for developers to kind of try out Trainium and Inferentia, but at the same time have the ability to kind of move to a different architectural platform if it suits their needs better, right? So we had a very strong focus on taking our IP and plugging it under open source frameworks, right? And helping customers leverage those open source frameworks enables them to actually, have that level of abstraction, right? So that's one key thing. There's a similar concept on the Nitro side, and I know you guys got to see some of our Nitro cards also. So Nitro, for the most part, is actually fully transparent to our customers. Like our customers, in many cases, don't directly leverage Nitro. Like it's a behind the scenes technologies that provides a lot of value, right? And that enables our customers to kind of maximize how much hardware they're able to use and essentially the value they're able to get out of AWS, right? So there are different ways for us to enable our customers to leverage the capabilities we have on the hardware side. On the Nitro side, it's transparent for the most part. And then specifically on the training and inferentia side, it's by enabling our customers to use open source frameworks instead of directly building on top of a compiler technology, right?
And I really like that introduction of Nitro into the story because everyone's like AI, ML, everything. But Annapurna Labs, the first chip that kind of came out of there was Nitro, correct?
Yeah, you're absolutely right. Yeah, so our journey with building silicon for AWS started with Nitro, right? And it goes back to like 2015, 2016, as you mentioned earlier. And the way we virtualize our hardware is at this current point in time 100% managed by Nitro. So let me rewind a bit, right? So prior to Nitro and prior to us building our own silicon, on the hypervisor side and how we managed to enable customers to run on slices of servers, a lot of that management was actually running on the same server itself, right? So that's typically how hypervisors work, where you would take out like 15, 20% of the compute resources on the server itself and allocate it for management purposes, and then you have the remaining part of the compute available for you to run customer workloads, right? So Nitro as a core capability enabled us to like offload a lot of the management capabilities and all of it and run it on a dedicated card. And that's where we started building our own chips. There wasn't off-the-shelf accelerator that was available for us to run our own management stack. And that's where we started building our own Nitro chips, our own offload cards, and plugging them into our servers, right? So Nitro has actually laid the foundation when it comes to like building expertise around silicon. We built on it to launch our Graviton CPUs, about 4 years back, right? And that was super exciting because, again, that was the first time in the industry a cloud provider had built a CPU from the ground up and brought it to market, right? And then we built on that capability of being able to kind of build high-performance CPUs, start building accelerators for AI/ML, hence Trainium and Inferentia were kind of born. And now we are on our third architecture for Trainium and Inferentia. So it's been a fascinating ride.
Yeah, and fascinating for me as well. So thank you so much for taking time to chat with me today. Are there any last thoughts that you want to leave folks with?
No, I think it's super exciting chatting with you. And, we spent a bunch of time talking about, silicon, which is a core part of what sets AWS apart. But at the same time, if you look at everything else we have to offer in our portfolio, from storage products, networking products, and all the high-level managed services, we think we have a really compelling portfolio for developers to kind of build their Gen AI applications, and silicon and hardware is going to underpower all of this, right? So again, there's a lot of stuff we're working on, and we're looking forward to sharing some of these details in the coming months with you guys, and obviously with your customers and your developers. Right? So.
Well, we're looking forward to hearing those stories. Thank you again.
All right. Thanks for the time.